Hello everyone. Well, it looks like you've made it to the last video lecture of Chapter 1. So in the previous lectures for Chapter 1, our focus was about measuring matter. That's what we're looking at, whether we were, making measurements, sig figs, precision, looking at more specific things like units and unit conversions, volume, density, temperature. All of it was about measurement. Well, now we're moving away from measurement. We're, instead of measuring matter, now going to review how we describe matter and its changes. Describing matter and its changes is the topic of this lecture. So the place we're going to begin with is by taking a look at how to describe the physical states of matter. And as it turns out, one thing we already know, of course, is that pure matter occurs naturally in either the solid, liquid, or gaseous states. Quick note, what do I mean by naturally? Well, naturally, I typically mean by at room temperature and pressure. Let's write that here. At room temperature and pressure. Which of course leads to another question. What's room temperature and pressure? Room temperature is 25 degrees Celsius. Room pressure, 1 atmosphere. So under these conditions, we find pure matter in any one of these three states, solid, liquid, or gas. Let's take a look at some examples. So if we were looking at some examples of pure matter that exists in the solid state naturally, well, solids would include things like, well, our metals, all metals, except for one, which is mercury, are solids at room temperature and pressure. So let's write all metals except mercury. You might remember mercury symbol is Hg. Okay. All salts are ionic compounds. All ionic compounds, all right, which you could say are salts and or minerals, are solids at room temperature and pressure. Glass and all types of glasses are solids at room temperature and pressure. Plastics, woods, etc. are all good examples of substances that we find naturally in the solid state. Well, what about substances that we naturally find in the liquid state? Well, liquids might include, well, of course, the most ubiquitous liquid of all, water, okay? Or perhaps we could look at something like ethanol, which naturally occurs as a liquid, or acetone. Oils, of course, all occur as liquids. Mercury is a liquid at room temperature and pressure, etc., etc. So again, just some examples of naturally occurring liquids. And let's bring up the rear with some examples for gases that exist naturally at room temperature and pressure. And I'm sure you can think of many gases. Are oxygen gas, methane gas, helium gas, nitrogen gas, carbon dioxide gas, etc., etc. So lots of examples of substances existing naturally as solids, liquids, or gases. At extremely high temperatures, you get another state of matter. It's called a plasma, but again, we're talking about room temperature and pressure here. Okay? Now, how do we describe physical states? Well, it depends whether we're looking at the physical states on a macroscopic level or on a molecular or atomic level. Okay. The macroscopic level is the level at which you and I exist. So if we're going to describe solids, liquids, and gases on a macroscopic level, what we're doing is describing what we see and what we can measure. And so what do we notice? Well, solids are described as rigid. They have fixed volumes and fixed shapes. Liquids, however, are described as fluids. Liquids have fixed volumes, but they don't have fixed shapes. They instead take on the shape of whatever container they're occupying. So if you pour a liquid into a tall cylindrical glass, the shape of the liquid is a tall cylinder. But if you take that liquid and then pour it on the ground, what shape does it have now? It has the shape of a puddle. But whether it's in the puddle or it's in the glass, it has the same volume. It's a fixed volume. Now, gases are also described as fluid, but they have neither a fixed volume nor a fixed shape. And that's because gases expand or contract to entirely occupy their container, which means gases will always take on both the volume and the shape of their container. Okay. Solids have very high densities and low compressibility. What does low compressibility mean? It means it's hard to take a solid and pressurize it and force that solid into a smaller space. You can't do that very well with solids. Now, gases are the exact opposite. They have low densities but high compressibility, whereas liquids have densities and compressibilities in between those of solids and gases. Okay. Well, those are some very basic things we can say about solids, liquids, and gases on a macroscopic level. Well, what about describing physical states on an atomic or molecular level? In other words, how are the particles of solids, the particles of liquids, the particles of gases behaving? Okay, now we can't see that, but all right, we know they're behaving in specific ways, and the ways that the particles of matter behave affect the things that we can see, observe, and measure. So what about solids? Well, turns out that in solids, the particles are packed very closely together. They're close packed and they have very, very limited freedom of motion. In fact, the particles in a solid can only vibrate back and forth about a fixed position. So let's make a note of this. So here our particles are close packed and can only vibrate back and forth, vibrate about a fixed position. So that's the best the particles can do, back and forth, vibrating about their fixed positions. Now, in a liquid, the particles are still pretty close packed, but not quite as close packed as the particles are in a solid. But the real big difference we see with liquids is not so much the spacing, but the freedom of motion. Turns out that the particles of a liquid can move about, all right, to a greater extent than the particles in a solid. They're no longer in that fixed position vibrating. They've broken free of these fixed positions and are moving around to some extent. So let's note here that the particles are still close, but can move around to some extent. Okay. Okay, and that takes us to the gaseous state of matter. Well, in the gaseous state of matter, the particles are really far apart, very far apart. In fact, this figure here does not even come close to truly illustrating how far apart those gas particles. They are very far apart. Not only are they very far apart, they're moving extremely quickly in random directions. So I'm going to write that here. Particles very far apart, moving quickly and in random directions. Okay, to do a quick comparison, to give you sort of a visual on this, let's suppose instead of doing this video lecture, I was in the classroom with all of my students, and all of my students were sitting at their assigned desks. Okay, well, sitting in the desk, the whole classroom, if each person in the room represented a particle of matter, if you're all sitting at your desks, you're rather like a solid. All right, you have fixed positions and you don't have a lot of movement when you're sitting in your desks. You have a small amount of movement. You're writing, you're twitching, you're fidgeting, but you look like a solid. Okay. Now, if I wanted to turn you into a liquid, all right, still in the same classroom, I would ask everybody to get up and walk around. Now, as you're walking around in the classroom, you are now more like a liquid. Everybody is still pretty close together. You're probably bumping into each other a little bit, but you have greater range of motion. And clearly, it's a more chaotic state than the solid when you were all sitting at the desks. Now, if I wanted to then turn you into a gas, I would say class is dismissed. And if I say class is dismissed, everybody starts running to get out of class, okay, because they have another class to go to, or they want to beat the traffic on the freeway, or they really want to start studying chemistry in the library. And in very short time, everyone in the classroom is now really far apart, moving in random directions, and now you're like a gas. Okay, so it turns out that matter can always undergo a change of state, all right, simply by changing the temperature that the matter is subjected to or the pressure that matter is subjected to. So if we have a substance and we change its temperature or pressure, it could undergo a change of state. And I should note that a change of state is also known as, AKA is an abbreviation for also known as, all right, a phase change. So they mean the same thing. Phase change, change of state. So let's review what those changes of state are all about. Well, we might recall that a solid, all right, when it converts to a liquid is said to be melting. But if the liquid goes back to the solid, it is freezing. Meanwhile, if the liquid converts to a gas, well, that is the process of vaporization. And the reverse process, a gas, all right, converting back to a liquid, is condensation. Now, under certain conditions, the liquid state can be bypassed entirely, and a solid can convert directly to a gas via the process of sublimation. And the return journey, gas bypassing the liquid all the way to the solid state, this was a process called deposition. So how do temperature and pressure changes cause these changes of state, these phase changes? Let's take a look at the next page here. Well, let's suppose we gradually increase the temperature on a substance. That's what we're doing here. So if the temperature on a substance is gradually increased, let's highlight that. Temperature of a substance is increased. Well, what do we notice in terms of phase changes? Well, what we see is that solids will eventually convert into liquids, and liquids will eventually convert into gases. So what's going on here to cause these observed changes? Well, we've seen in previous lectures that temperature has an effect on the kinetic energy of the particles of matter, that as temperature goes up, the kinetic energy goes up, and the particles move faster. Now, if the particles move faster, all right, they're going to separate further apart. And if they're separating further apart, well, solids can become liquids and liquids can become gases as the separation between the particles increases along with their molecular motion. So let's note over here that as temperature goes up, we see that particles of matter ultimately move faster and separate more, which is the logical outcome. Separate more. Okay. Well, now let's see what happens when we change the pressure that is applied to a substance. So, if the pressure on a substance is increased, well, what happens? Well, we actually see the opposite. When the pressure on a substance is increased, gases convert to liquids, and liquids convert to gas. So, liquids convert to solids. So gases convert to liquids, liquids convert to solids. So what's going on in this case? Well, as we increase the pressure on a substance, what happens is that the particles of matter get forced closer together. And if they're getting forced closer together, those gases with the particles far apart get squeezed. The particles get closer and closer together until you've got a liquid. And if you keep squeezing on the liquid, the particles get closer and closer together until you've now created a solid. So let's note over here that the particles are forced closer together. Okay. And of of course, the opposite is true. So if you increase the pressure and you see changes in one direction, a decrease in pressure is going to have the changes taking place in the opposite direction. Same for the temperature. Okay, so we've taken a little bit of a review of our states of matter. Well, now let's review pure substances and mixtures and make sure we understand how they are different from one another. So all matter may be classified as either a pure substance or a mixture. So we're going to start with pure substances and what they are. So pure substances are composed of just one component only, one component only. And what components are possible for a substance to be pure substances? For a substance to be pure, I should say. Well, a pure substance will either be an element or a compound. That's it. Elements or compounds, these are the only types of pure substances. So, elements, you may recall, are the simplest type of pure substance, and they cannot be broken down to anything simpler by chemical processes. And if we take a look at elements on a microscopic level, all right, we see that elements all consist of the same atoms. So obviously we can see the periodic table for numerous examples of pure elements. So I can put that C, periodic table. But if we just want to write down just a few examples here of pure elements, of course, you can probably name many upon many pure elements. Well, gold is a pure element. Oxygen is a pure element. Silicon is a pure element. Neon is a pure element. Chlorine is a pure element. Potassium is a pure element. Uranium is a pure element. Of course, we can keep going and going and going. Let's add maybe just a couple more. So carbon is a pure element. Let's just add one more. How about bromine is a pure element? Okay. Um, we're going to talk about elements in quite a lot of detail when we get to chapter 2. The same is true of compounds. We're going to also be going over compounds very much in detail when we get to chapter 2 as well. So what are compounds? Well, compounds are formed by the chemical combination of two or more elements in fixed proportions. And these elements that you find in compounds are chemically bonded together. So let's make a note that these elements here are bonded together. Bonded together. Okay, so what are some examples of compounds? Well, let's take something as simple as water, H2O. H2O is formed by the chemical combination of hydrogen and oxygen. And these elements in any sample of water that you get from anywhere are always in fixed proportions. It's always 11% hydrogen and 89% oxygen in any sample of water. Or maybe, for example, salt, sodium chloride. Sodium chloride is a compound formed by the chemical combination of sodium and chlorine, elements sodium and chlorine. And in sodium chloride, the percentage of of sodium is always 39%, and the percentage of chlorine always 61% in every pure sample of salt. Now, obviously, you can think of many examples of compounds that we could list here. Let's just put a few. Oh, I don't know. Aluminum sulfate is a good compound we could write here. Phosphorus pentafluoride is a compound we could write here. C12 H22O11. There's a good compound for you. That's sugar, of course. And, well, obviously, we could keep going and going and going, just like we could have done that over here for our elements. Okay, so we've taken a quick look at elements and compounds. Well, what about mixtures? So a mixture, as it says here, is formed by not the chemical combination, but the physical combination of two or more pure substances. Those pure substances could be two or more elements, two or more compounds, or elements with compounds. Now, the key here is the substances in a mixture are not bonded together. So I'm just going to write down not bonded together. Oops, not quite writing that correctly. Let's try again. Not bonded together. Also, unlike compounds, the proportion of the substances in mixtures are variable. They're not fixed. So, in other words, you could have a mixture of salt and water, where the amount of water is 50% and the amount of salt is 50%. Or you could change it up and have 10% salt, 90% water. All right, it doesn't matter. The proportions of substances in mixtures completely variable. Okay. Now, mixtures can be described as either being heterogeneous, whoops, or homogeneous. So what's the difference? Well, we have some descriptions here. A heterogeneous mixture has a non-uniform appearance, and individual components of the mixture are visible. In other words, we can look at a heterogeneous mixture and say, yeah, that's a mixture. We can look at it and recognize that it's a mixture because the parts are easy to identify. So if we want to put some examples here, maybe something like muddy water. All right, we can see the mud, all right, clearly different from the water. So the parts are clearly visible to us. Or perhaps something like, say, carbonated soda. So carbonated soda, we can see the bubble part different from the soda part. Different components of the mixture are visible to us. Or perhaps we could take something like, say, a salad dressing. So salad dressing, the watery part is clearly different from the oily part, which is different from any of the spices you might see floating around in the salad dressing. These are all good examples of heterogeneous mixtures. Well, what about homogeneous mixtures? Well, homogeneous mixtures have a uniform appearance, which means a homogeneous mixture doesn't necessarily look like a mixture. It might look pure. This is because the components cannot be distinguished from each other, and the reason for this is that they are evenly dispersed on a molecular level. So it's perfect mixing all the way down to the molecular level. So what sorts of mixtures could be classified as homogeneous mixtures? Well, turns out that all gas mixtures are homogeneous mixtures. If you have a mixture of two or more gases, it is automatically a homogeneous mixture. So, for example, if you have a mixture of helium and oxygen, which you might find in, say, a scuba tank, well, that mixture of helium gas and oxygen gas is automatically a homogeneous mixture. Or say natural gas, which you find in Bunsen burners. Natural gas is a mixture of mostly methane gas and ethane gas. It's a homogeneous mixture. Air is a homogeneous mixture. It's a mixture of nitrogen and oxygen and lots of other gases as well, but mainly nitrogen and oxygen. It's a homogeneous mixture. Okay. What else is a homogeneous mixture? All solutions are homogeneous mixtures. If it's a solution, it's a homogeneous mixture. So, for example, Gatorade. Okay, Gatorade is a solution in which you've got sugars, you've got electrolytes, you've got flavorings, all dissolved in water. And when you look at that solution of Gatorade, you can't point to the sugar section and the electrolyte section and the flavor section. It's all indistinguishable. It looks like one substance. Or, for example, alcoholic beverages, say like vodka. Vodka is mostly a solution of water and ethanol. And again, when you look at the vodka in the shot glass, not that you're having vodka shots or anything, or maybe you are, I don't know. Maybe you needed to get through the chemistry. No, you're not doing that. But you can't tell the water part from the vodka part, right? Sorry, water part from the ethanol part, because they're mixed, they're evenly dispersed down to the molecular level. Okay, and another important type of homogeneous mixture are metal alloys. Metal alloys are created by mixing two or more metals together. Now, metals are normally solids, so to create a metal alloy, you would have to melt the metals, then mix them together homogeneously and let them, all right, reform as a solid, and as the solid, they're now metal alloys. So for an example, something like, say, brass. Brass handles, brass doorknobs, for example, which is a mixture of copper and zinc. Okay. Stainless steel, if you have stainless steel knives or spoons in your kitchen, well, stainless steel is also a metal alloy. 14 karat gold is actually a metal alloy as well. So there you have it, some homogeneous mixtures, some important examples of homogeneous mixtures versus some examples of heterogeneous mixtures. Okay, so moving on. I said this section is not just describing matter, but the changes that matter undergoes. And those changes can be described as either physical or chemical changes. So what's a physical change? Well, during a physical change, matter undergoes a change in its form, but not its composition. Another way to say that is the chemical identity of matter remains intact. And these changes are typically very easy to reverse. So what are some examples of physical changes? Well, one important category of physical changes are changes of state. All changes of state, all phase changes are automatically physical changes. They're automatically physical changes. Well, let's think about it. Let's just draw a little picture here. So let's suppose I have some ice. I'll draw a cube of ice here. That's not so bad. There's ice. Well, we could take that ice and melt it, and it would become water. So here's our water. That's a really bad picture. Let's try again. All right, here's my glass. Here's the water. I'm not sure that's, oh boy, that's not a whole lot better, but you can do better than I did. So we have our picture of water, and of course we could heat it up, and well, it could turn into steam. Let's see, how should I draw steam? I'll know, I'll draw a cloud. Here we go, a cloud of steam. Okay, and of course, this is reversible. We can condense the steam back into water. We can freeze the water, get back our ice cubes. Now, what's going on here? Well, the form of matter is changing. Ice looks different from steam, which looks different from water. They are having a change in form, but the composition, chemical identity remains intact. Well, what's staying the same? The molecules are staying the same. So ice is composed of H2O molecules, so is water, and so is steam. The water molecules remain intact. Um, in the solid state, they're packed close together, but further apart in the liquid and even further apart in the gas state. So let's note here that the molecules remain intact. Let's write unchanged. So the form undergoes a change, but not the composition, not the building blocks. Now, another important example of a physical change that we see in chemistry are whenever we dissolve a substance in water. So dissolving substances in water is also considered a physical change. So for example, let's suppose you had some sugar. So sugar, also known as sucrose, is C12H22O11. And in its natural state, it's a solid. It's a solid. It's a white crystalline solid. Now, we know that sugar is soluble in water. It dissolves readily in water. And when it dissolves in water, it changes its form. You no longer see the sugar as white and crystalline and solid anymore. So when you dissolve it in water, well, it's not the same as before. What state is the sugar or any substance when we dissolve it? Well, it enters into the aqueous state. Let's write this over here, aqueous. state, where all the sugar molecules become dispersed in the water. Okay. Now this is a physical change because we observe a change in form, but the molecules of sugar remain intact. And this is also a reversible process, a fairly easy process to reverse. All right, if you have sugar dissolved in water, you can vaporize the water and get back the crystals of sugar. So no chemical alteration has taken place. Now, let's take a look at chemical changes. During a chemical change, well, on a chemical change, matter undergoes a change in its composition. So this time we have a change in composition and form. Usually a change in form occurs whenever composition changes. We know that initial substances are converted to new substances, and more often than not, these changes are difficult, often impossible to reverse. Okay, let's remember that we tend to call these initial substances reactants and the new substances products. And of course, we're going to be looking at many upon many chemical changes as we progress in this chapter. Let's look at some basic everyday chemical changes that occur around you. So for example, burning. Burning what? Burning anything. Let's say burning wood. Burning wood. Burning gasoline, burning candle wax, burning anything, of course, is a chemical change. Wood reacts with oxygen, leaving what? Well, you make ash, carbon dioxide, water vapor, and I've never seen anybody take ash, carbon dioxide, and water vapor and turn it back into wood. That would be quite a feat, I think. Okay, what else? Well, we could take a nail rusting, a steel nail rusts is a good example of a chemical change. Or perhaps, say, sugars becoming fermented into alcohol. Sugars ferment into alcohol. There's a good example of a chemical change. Or perhaps acids neutralizing bases. That's another chemical change for you. And of course, we can keep going. You can probably think of many examples of chemical changes, different types of reactions that you've studied that are all examples of chemical changes. So for example, TNT exploding. TNT, where is it? Explodes. Here we go. These are all good examples of chemical changes. Okay, now let's talk about the properties of matter. So the properties of matter, the word properties, when we talk about the properties of matter, properties refer to characteristics of matter, unique characteristics of matter that can be used to identify matter. And the properties of matter can also be classified as either physical properties or chemical properties. So physical properties are properties of a substance that may be measured or observed without changing the fundamental composition of the substance. Okay, so what are some good examples of physical properties of matter? Well, good examples would include things like the melting point of matter. Melting point. So when we melt a substance, all right, the temperature at which a solid becomes a liquid is characteristic to all pure substances. Now, when we melt a substance, convert from solid to a liquid, we are not altering the composition of a substance. The molecules remain intact when we melt. Likewise, boiling point is a good example of a physical property of matter for the same reason. Boiling point, the temperature at which a liquid boils and turns into a gas under normal atmospheric conditions. Or density, the density of a substance is a physical property of a substance. We've seen before in our lecture on density that all pure substances have unique densities. If we want to get the density of a substance, we have to measure its mass and volume. Measuring mass and volume do not alter the composition of a substance. It stays the same. So the composition stays the same. Other examples that we could add here, solubility, whether or not a substance dissolves in water. Or you might remember this one from Chem 10. We'll certainly review it later. Specific heat capacity is a good example of a physical property of a substance, or whether or not that substance exhibits magnetic behavior, etc., etc. Some simple examples of physical properties of matter. Now, what about chemical properties of matter? Well, chemical properties are actually chemical reactions. They are chemical reactions that are characteristic of a particular substance, or that they are unique for a particular substance. Now, since reactions are involved, the composition of a substance will be changed upon observing its chemical properties. So, for example, let's suppose we had a sample of ethanol, liquid, and a sample of water, liquid, both liquids at room temperature and pressure. Well, if we wanted to identify ethanol versus water using physical properties, I don't know, maybe we could measure their densities, we'd see a difference. We could measure their boiling points and see a difference. But there are other ways to check, all right, their differences. And one way is to use a chemical reaction. And of course, ethanol burns. So if we put a lit match in the ethanol, it'll light up. But if you put a lit match in water, it does not burn. So this is the way a chemical reaction, all right, can tell the two substances apart. The fact that ethanol burns or is flammable is a chemical property of ethanol, one that is not shared with water. Or we could take another example. Let's do another example. Say we had baking powder versus sugar. Maybe we're in the kitchen. Okay. And well, baking powder will bubble if you add acid. Bubbles when adding acid. But sugar does not. So again, this would be a way to use a chemical reaction, distinguish between the two. Bubbling when adding acid is a chemical property of baking soda. Or perhaps if we had two metals, sodium metal and zinc metal. Okay, well, if you put zinc metal in water, nothing happens. If you put sodium metal in water, it explodes. So, all right, the explosiveness of sodium in water is a chemical property of sodium. So on and so forth. So let's just put etc. over here. Okay, so this brings us to the very last little topic here, describing the properties of matter as either intensive properties or as extensive properties of matter. So let's start with intensive properties. Intensive properties are properties of matter that remain the same even when the amount of matter is changed. So I'm going to give us some examples of intensive properties here. So good examples of intensive properties would include things like temperature or melting point or boiling point. Whoops, that's not how you write that. Let's try that again. Excuse me. Melting point, boiling point, density. These are all good examples of properties of matter that stay the same even when the amount of matter is changed, that is increased or decreased. So for example, let's suppose I have a piece of aluminum, a teeny tiny piece of aluminum. And let's suppose I have another piece of aluminum. Let's suppose I have a much, much bigger piece of aluminum. In other words, I have changed the amount of matter. I've increased the amount of matter. Well, what's going to stay the same about both of these pieces? Well, for example, the melting point is going to be the same, regardless of whether I have a tiny piece or a big piece. Turns out that the melting point of aluminum is about 660 degrees Celsius. So melting point is 660 degrees Celsius for the small piece. And the melting point is the same for the large piece. It's still 60 degrees Celsius. Okay? The density of the small piece and the density of the large piece is the same. The density of the small piece is 2.7 grams per milliliter. The density of the large piece is still 2.7 grams per milliliter. So this is what we mean when we say a property is intensive. All right, the property remains the same even when the amount of matter is changed. Another way to say that is that an intensive property is quantity independent. Quantity independent. And if it's not intensive, the property is extensive. So an extensive property is a property of matter that does change when the amount of matter is changed. So good examples of extensive properties would be things like, say, mass and volume, which is rather easy to see. If we go back to our example of aluminum here, and I have a small piece of aluminum versus a large piece of aluminum, well, are these two pieces of aluminum going to have the same mass? No, the mass is going to be different. All right, more matter, more mass. Same with the volume, more matter usually occupies a greater volume. So over here, the mass of the small piece, so let's just arbitrarily say the mass of the small piece is 5 grams. Let's make the mass of the bigger piece 10 times that, 50 grams. Okay, the volume of the small piece, well, a 5-gram sample of aluminum would be about 1.9 milliliter volume, and the volume of the larger piece, 19 milliliters more or less. So clearly, the amount of matter, all right, affects an extensive property. Extensive property changes as the amount of matter changes. And another way to say this is that an extensive property is quantity dependent. Quantity dependent. Okay, so we are now completely finished with this last lecture, this last part of chapter 1. We are now finished with chapter 1. So well done. You've done a great start, and I'm looking forward to jumping in our next lecture, chapter 2 material. Okay, make sure that you're keeping up with the practice problems that are assigned. Do not fall behind. The only way you really can test your understanding of what I've been covering with you in these lectures is to do the practice problems. Okay, everyone, take care. Hope you're well, hope you're safe, and I'll talk to you soon. Bye now.